Just like momentum is conserved translationally when one cart smashes into another cart, we know that the momentum before and after the collision will be the same. The same is true angularly. Angular momentum is L, and L equals I omega. And as long as we have a closed, isolated system, no outside forces act and no mass is allowed to exit or enter, then angular momentum is conserved. And I think maybe we're going to do an example problem where what we would have is, imagine that I have a long thin rod suspended about its axis, about its center. So it's got like this little bolt through it, and we're going to take and we're going to hang that thing, and we're going to allow it to be suspended so that it can spin. So from a top-down perspective, I have the cylinder, there's a little bolt here, it's connected, and this thing is allowed to rotate. Now what we're going to do is we're going to actually, it can pivot here as well. So it can rotate vertically straight up and down, or we could let it pivot and then it would be laying horizontally and it would be rotating about its axis here. So in one instance, it's rotating about its vertical axis, and then we allow that rod to pivot, and then it's rotating, but it's rotating, now it's rotating around its axis of rotation the other way. And so essentially what I've changed it here is from a cylinder rotating to its a long thin rod. Okay, and so let's say that at the beginning it was rotating, it had an angular velocity of, say, 3 radians per second. What is its angular velocity after it lays down flat and it's rotating this way? Well, what did we do? Well, what we did was we changed the distribution of the mass about the axis of rotation. We changed its moment of inertia. So in the first case, where it's a vertical rod and it's spinning about its center, that has a moment of inertia equal to 1/2 mr squared, because we think of it as a solid disk, right? If we were looking down from it at the top, there's a solid disk, and that mass is distributed around its axis of rotation, so 1/2 mr squared. However, over here, when we changed the moment of inertia to being about a long thin rod, now our moment of inertia is 1/12 ml squared. And if this rod had a radius of 1 centimeter and a length of 14 centimeters, then we can answer this question. So what we know is initially the angular momentum is 3 times 1/2 times mr squared. And r is, I'm going to leave it in centimeters, 1 squared. This has to equal its angular momentum afterwards because there was no outside forces. This thing just laid over. And so this would be equal to omega times 1/12 m times L squared. And L is 14. I'm going to go ahead and leave it as centimeters. And I can leave it as centimeters because we're going to divide them out and it's not going to matter. So I have 3/2 m equals omega times 196 over 2m. The m's cancel, it's on both sides, so I have 3/2 m, right? 14 squared is 196, so equals 98 omega, and I can divide both sides by 98 and get 3 over 196 equals omega. And so this thing gets quite a bit slower, and the reason it gets so much slower is because there's a whole lot more mass now that is distributed outside of the axis of rotation quite a bit further away.